This one. Good evening, everybody. So let us start our lecture tonight. And I think this will be a short lecture today. An hour should be fine. Today is September 23rd, right? So in next lecture, September 28, it will be your test one, right? There is no lecture, but this test. So you will come here. I will give you exam copy, and then just you bring paper, pencil, and eraser, and whatever your book, and then whatever your printed materials, but no device, please. Okay. So actually, it is a great challenge to write test questions for open book test. So the test questions, if you are familiar with the stuffs that whatever we covered in our lectures, and then in our class activities, in our assignments and quizzes, you will be good. But if you plan that, if you think that, oh, it is a open book test, I don't need to study, that will be a mistake for you. So in the test, time is limited. There are 6 or 7 questions for 75 minutes. So you should not be think to read the book and understand and then write. You should not be able. My thinking is that you don't need to memorize anything. If you forget the steps, then look at the book and quickly, or your notes, then quickly get that. Okay. So hopefully, if you give attention to my lecture and then other stuff, then you will be good. You should be good. Okay. In our last lecture, we were discussing data structure. That means elementary, or it's called elementary data structure. I don't know why it's called elementary. So the book says elementary data structures. So that by elementary data structure, I understand actually array, mainly arrays. Okay, and then the book is cover also arrays, linked list, stack, and queue. Actually, stack is useful. Mainly, stack is useful for operation. Whenever we do program execution, programs like values, temporary values are put on stack and then get from stack. So program execution goes through that way. I think if you should have learned that in your data structure course. We did not cover that in this course. So in our last lecture, we covered almost all of these basic data structure: linked list, stack, queue. Okay. And we stopped at BST, binary search tree. Okay. So at that time I did not have a chance to open the book. Now today I will spend some time opening the book. So in the book, so if you please read the book, okay, and the book, so please read that. And for instance, some things, but there are some instructions over here. Let us review quickly. So this course is algorithm analysis. So we will analyze our code. So for each of something, for instance, push operation and pop operation. For every algorithm, we should know the running time or complexity. So for push, what is the running time or complexity? What do you think? For push operation over here. Push means the S is a stack, S is a value. Okay, that will push it on the top, right? So what is the running time or time required for this kind of operation?
Linear?
Huh?
Would you say linear? Because
not linear.
Constant.
Constant. Okay. Similarly, for pop operation, you see there is a if statement and else statement. That takes some time to execute, right? But compared to our data size, we say linear. That means if the time increases linearly, data size increases, time increases. Data size becomes lower, time becomes lower. That is linear, okay?
Yes, sir.
And there is a like steady ratio. But for this one, push and pop, you see there is no that kind of. One thing is to remember that trick is that look for the loop. Okay, if there is a loop, any kind of for loop or any kind of loop, you may know that there are some examples that without any even for loop, there can be with if and else, you can make a loop with even if else. So not necessarily that you have to have for loop or while loop or do while. Without the program structure, for instance, if else, you can make a loop with if else. If I have time, I will show you an example how to do that. Okay, but for this one, so do we have any loop? No. So then constant time. Constant time, it is defined is big O1. It does not mean that it takes 1 millisecond. It takes constant time. No matter it does not relate with any data size. No relation with n. Whatever n, this no matter, because we know the stack stop value. Push is go on the top and pop goes on the top, right? So it does not matter where is how many data elements exist. So this is called big O 1 times. From the book, when you read the books, it's color, mark all of these time complexity. Go through this, okay? And similarly for QE has two main operations, NQ and DQ. Okay, for NQ and DQ, there is no loop, right? So then since that time operation big O1, and if there is a one loop, either for loop or while loop, then linear, big O(n), or sometimes called theta n, or if there is an inner loop inside an outer loop, then big O(n) squared, right? So here there is no loop. So your task is for stack QE and linked list, look for this type of code, okay, and search for the running time, complexity of an algorithm. For this one, what will be the complexity of this algorithm? The search operation. Who can tell me? Adam? Yes, big O(n), because there is only one loop. What it is doing, it is going to starting from the head, and it is going to all the way end, searching an element. If the element is at top, then it's fine. But unluckily, or in the worst case, we are looking for worst case. Or in the another case, if the element does not exist, right? If an element does not exist in a linked list, still we have to go all the way end, right? By looking a few, we cannot tell that the element does not exist. Still, we need to go all the way in. Or if the element it exists, it may be the all the way last element, right? So in that case, you need to go through all the way. And so if your linked list size increases, it will take more time. Size decreases, it will take less time. Okay, so this is why it takes equal theta n. Okay, and for other operations, for instance here, so this one is insert. Okay, if it's insert, then insert operation is it takes. Sometimes it depends where are you inserting. If you insert on the top, then it takes some time. If you insert all the way end, then it takes time. Right, you need to go to all the way end. So insertion operation, it depends on the situation. Okay, and delete, where are you deleting from? Are you deleting the head, or are you deleting the last element, or any middle element? That depends linearly. Okay, so in the worst case, it takes theta n time, but in the best case, theta 1, that element is a drop. Okay, please go through this book and then please understand those. Okay, so if you don't understand anything, please, I think it should be straightforward and you should know. Okay, then in our at the end of our last lecture, we discussed binary search tree, right? So we discussed BST, So a binary, actually we discussed tree. Okay, this is the homework I want to give you. Please mark on your paper. This is a homework. This is your homework. Okay, you please do this at home. Please try it. Or do it. Okay. Do it at home. So write number exercise 10.4.1.
So I noticed with this textbook there aren't like answers in the back, so we can like check our solutions.
Yes, you can do.
Do you know if there are answers anywhere where we can kind of check if we're?
I think you do if you Google search, then you will get it.
You can Google it. There's a website that has all the answers. I don't remember what website it is, but when you Google it, someone will come up and you can select the chapters and sections within each chapter.
Cool. Okay.
Okay, but try it yourself. Okay.
Okay.
Okay. In the test, if you get a this kind of questions, so if you practice it, then you will be able to do it quickly. Okay, there's one more I want to give you as a homework task. Complete this one also. Complete this table in your book. Complete this and then fill this out. Okay, and spend some time.
What number is that?
This number is 10.1. It's 10.1. Problem. Okay, then as I said at the end of our last lecture, we discussed what is that BST, binary search tree. Come on the list. What is that one? Okay. Okay, maybe I have a note. Let me open slides from. Through additional PDF slides. You should have binary search tree. Okay, let us see that what we have here at the end of last chapter. We discuss all of these. I'm looking for BST. No, it is not here, sorry. Where should it be? These one should be. Okay, so let me discuss the concept. So at the end of our last lecture, we discussed BST, binary search tree, right? The structure of binary search tree is that every node, if there is if a node exists, it node contains child, then there will be maximum 2 children, right? Okay, if there are child, then maximum 2 children. And BST has condition this value, say 45, the top head value or parent value. Every left child has value less than its parent value, and right child has value is greater than its parent value. For instance, for 50, like this. Okay, if there exists child, then there will be at most 2 child, not more than 2. Okay, 2 conditions, right? So all of this fulfilled. So this 45, 40 and 50. Okay, so if there is no child, then fine. If there are children, then at most 2, either 1 or 2. Okay, but we saw that regular, so this is regular, this format is regular BST, and it has some features that height is say height h equal to, or lowercase h equal to log LG log n with base 2 for BST, binary search tree, right? But it is not always true. It may happen that you got a BST, you got some data element, like for instance, first element is 45. Okay, then second element you got more than 45, 50. So that it go right side, right? Okay, it will go right side, 50. And the third element you got 55. Then it will go right side of 50, right? So this element 55. And then fourth element you got 60. So still it is going to right side. And then last element you got 70 or 75, for instance 70. Then if this tree, this BST is growing linearly, right? Instead of this kind of standard structure, it is going to be a like linked list structure. So we saw that a few minutes ago. In a linked list, the search operation, it takes big O(n) time, right? Okay, so theta n times, so it takes theta n times. But this one, it will take log n time, in log n time. But every time it is split in half, right? But in order to check on it, okay. So this is one case. Similarly, another case, it should be here. For instance, if you have another data set, for instance, you got 40 first element, and second element you got 35, so it will get left. Next element you got 30, and the next element you got 20. So this is also linearly growing, right? So all this right, in this case right children are empty, and in that first case left children are empty, null, right? So in that case, both in this situation and this situation, it will take linear time. It may happen, right? So that means in that case it is not giving us any expected like running time or flexibility, right? So in that case, what should we do? There are other kinds of trees. Okay, that trees ensures balance. That's called balance tree. Ensure the balance tree, that ensures that a tree will not be growing like this linearly. Okay, first kind of this, there are two kinds of these trees well known. First of one is called red black tree. So the book mainly so red black tree is chapter 13. So if we go to chapter 13, red black tree. So is red black tree is a concept that it is a balanced, it will be balanced tree, balanced binary tree, and then it is balanced like this way. So that the root element is always black, the color, and there are some criteria. There are some features that root element is black, and then children is either black or red. So here in the book it is like black and white book. So this by gray color they mean red, and black is black. So there are some features for the red black tree. What are those? So some books has 4 or 5. These are the 5 features for properties for red black tree. We'll come here soon later. Okay. So the first one is that every node is either color red or black, nothing else. This is quite red black tree, and root is always black. Leaves are always null, blank or null. If a node is red, then the both children are black. If a node is red, then both children must be black. But if a node is black, then the children, at least one or two are both. Okay, in each node there is this path and descending leaves contain the same number of black nodes. Okay, but if it is black, then there is no restriction, such restriction. Its children can be black or can be red. But if it is red, both children must be red. And another thing is that either in both path, this path or any way you take path, any path you take, number of black nodes are same. So for instance, look at this one. So if you see, just look at this one. So if you say go this path, how many black children? 1, 2, 3, right? And if you go with this path, how many? 1, 2, 3. And if you go with this path, 1, 2, 3, 1, 2, 3, right? If you come with this path, 1, 2, 3, and if you come with this path, 1, 2, 3. If you come with this path, 1, 2, 3. If you come with this path, 1, 2, 3, and if you come with this path, 1, 2, 3. So when we develop our tree, there are few rules. There are some rules that if we maintain, then this kind of tree will be built. It's a little bit difficult. So in data structure course, maybe this is the one of the most difficult tasks I face. Red black tree. We will come later, but I will try my best to explain that. Okay, but in the book it has at the end maybe of this chapter, it is called AVL tree. AVL. Okay, AVL trees. So AVL trees, let us understand the AVL trees first. So by mistake I dropped AVL tree from here. I will add this one. Okay, so AVL tree should be here. So let us understand AVL tree first. If we understand AVL tree, then it's easy to understand red black tree. Okay, so AVL trees are coined by, are developed by some maybe then mathematician there, maybe Adelson. These are the name, maybe Russian people. Okay, so these are the people by their name who develop, who propose AVL trees, and by their name it is called AVL trees. So AVL trees, one of the things is that AVL trees, it is balanced or pretty balanced. Okay, it is balanced or pretty balanced. So how do we say pretty balanced or balanced? So we know the tree, like this is a tree, right? So we know the height, right? Did I discuss height or depth? So that if you take on a path from either direction, the maximum number of edges, this is edge, one edge, connecting, the connection between two nodes is called an edge. So right now, so far, we are not considering the edge values, but we will see at the end of this course some algorithms that where we value or we consider the length or the value of bit in edge values. Now we are thinking that this connection. Okay, so here the length is from root to leaf is 2, right? There's 2 steps, right? There are 2 edges, 1, 2. So this length is, this side length is 2, this side length is 2, and this side length is 3, right? So that one of the property in the AVL tree is that the difference between, right, for any node, you take any node, okay, the difference between the length in the right side, right subtree and left subtree, maximum 1, either 0 or 1. So in that case, what is the difference? What is the length? That's right, 3, right? And left side is 2. So difference is 1. It is fine. Okay. So it is fine, but in that case, one, 2, 3, 1, 2, and 1, 2, 3, 4. Let us come up with some example that is not AVL. Now maybe open the slides. Okay, now I open the slides. Let's have some examples. Okay, as I said that our motivation is to develop or build this kind of binary search tree instead of this. Okay, so then it will be pretty balanced, height will be pretty log n, and then searching time will be less. Okay, so let us see some examples that which is okay. So here in both sides is length is 2 and this side length is 2, so 2 minus 2 is 0, it is fine, it is AVL tree. And this side length is 1, 2, 3 and this side is 2, 3 minus 2 equal to 1, this is also fine. Okay, so these are the people, the humans who developed AVL tree. Let us come with an example. Okay, let us see on the right side, right on. This is not an AVL tree. Okay, the right side is length is 1, height is 1, right? And the left side 1, 2, 3. We will look for the maximum length. Height is maximum, right? So this side is 3 and this side is 1. So difference is 2, right? So this is unbalanced. So but this side is 2 and this side is 3. Is good, is balanced, or pretty balanced. Okay, and this is AVL tree, but that side is not. It is not AVL tree. Okay, you understand? Does anyone has any question? Okay, this is pretty straightforward, right? And maybe something interesting. So, in order to make sure that a tree is growing like an AVL tree, there are some rules. Okay, and let us see some examples, these algorithms in depth. we're not going through this algorithm, but let me illustrate this with some shell code. Okay, so let us start building a tree with some data inserting from 3 to 1. Okay, so the first data we got 3, right? So we put 3 over here. The second data we got 2, then 2 will go left side of 3, right? So this will be here. And then next data we got 1. Okay, so then this will be going this side. Okay, so instead of growing this, so actually the concept is like that. For instance, we will make it is balanced. Okay, think about that these edges are like a thread. These are a thread. Okay, and these are balls. These are balls. The ball number 3, ball number 2, and ball number 1. So how can we make a balance? So this is one-sided, right? So if you hold on over here on 3, then it will be length n. But if you hold in middle, okay, then it will be balanced. You see that this will hold on middle, and then these are string, so the one will go right side and then will go left side. Now instead of this, it looks better. It is balanced, right? So the rule is, the first rule is rule 1 is whenever you find it's a left and then another left, whenever you find left and then you will do, so I remember this way, you say left, then I will do rotate R, left, then R means rotate, straight, right. Adam, you have a question?
Oh, no, sorry.
Okay, no, it's okay. So then you will see that this one move right. Okay, so then this one go up, this one just move right. So then 3 will go over here, this side. Okay, so then first one is straightforward, rule 1. Okay, and then let us see other conditions. So if we proceed on, then we will see other condition situation. Now we insert 4, right? Then 4 will go on the right side of 3, right? Is good. There is no issue. Then inside, if you insert 5, okay, if you insert 5, then what will happen? Then 5 will go on the array, and this is the point it is making issue, right? So at this point it is making issue. It is good until 4, right? So at this point it is making issue. So here, so the condition over here, the rule 2 is we are getting right, then rotate left. Okay, so if you get right and right, I have right, this is right direction, and this is right direction. Okay, and take only the last 3, and then rotate. So I say L. Okay, I would write this one I would write like this one, R, LLR, rotate. Sorry, not rotate. Then right rotation. Right rotation. And then RR, you have existing R, then do left rotation. Rotation. So then if you do left rotation, is going right, you do left rotation. Okay, you do left rotation. That means if you do left rotation, that means 3 will come over here, and then 4 will go to 3. Okay, for instance, this one 3 will come over here and then enlarge the edge. So since we are not considering the edge length or value or weight, so this is fine, right? So it will be growing this way. Now it is good, right? So this situation was good, this was not good, this was not good, but after this rotation, right, left rotation, we got in good position, right? So there are 2 rules. If you get right after 2 left, you will not get 3 left, because there is no way. If you get 3, then we need to immediately rotate, right? So there is no way that you will get left. Only 2 left. Then you get, so for left, for instance here, if you got another left, then it will be fine. There is no issue over here, right? There is another thing we will discuss. Okay, so left. I did a mistake. So actually from here, right. So it should be 3L. Left is this one right. 3 1. There should be 3 right. Then you fix it, please. There will be 3, and the previous page there should be 3. Actually 3. We are considering from here to here. There are existing 2, and the next one is there are existing 2 right. Okay, so there is existing 2 right. This one right and this one right, and then if we encounter another right, then we will do left rotation. Okay, and previously I did a mistake. Let me go back to the previous slides. How can I go to the previous slide? Okay, there is left. So since 2, then we should do that. There is another. I will face another. Then we will discuss. Okay, so right. So there is left rotation. It's rule 3. There are 2 more rules. Okay, let us proceed on. Then we will find the situation. So this is fine. Okay, this has a special case over here. So this has a special case here. For instance, here you see that I need to erase these terms. Give attention here, please. This is the difficult task here to in this position. Initially it was up to this. When we insert 6, right? So this was right, and you do encounter another right. So here, so previously we considered only these 3, right? But those 3 were single. You see the look on here where there's no branch, right? But this one has branch already. Its root, grand root has branch. Okay, now so that our policy in the previous rule 2 was that if we encounter right, okay, okay, right, and again right. After 2 rights, if you get another right, then we say we do a left rotation, right? So then we do a left rotation, then 5 will go up, then 4 has another element. You see that 4 has another element. You see that 4, but that has a link with another branch. If this branch may be larger, here is this one child, it have more than. So then 4 cannot go alone. It will take with 3. It will take 3 with it, and that 3 will be on the left side of 4. Okay, so here what will be, so it's easy, this part was easy, 6 5 4. Okay, so 6 5 4, you see the 6 5 will go up, okay, and then 5 is going up, then 4, this 4 it is going root, and then think about this, these are string, okay. So then if you hold over here, okay, if you hold here, so then this 2 part will go down, right? This 2 node will go down, and this go on the left side. But on the left side, 3 is also greater than 2, right? 3 is also greater than 2. So then what will happen, this will be delinked, and there will be another link between 2 and I'm sorry, that will be not delinked. Sorry, this will create a link, this will be delinked, sorry, these will be delinked, so these will be delinked, okay, and then another link will be created between 2 and 3. This link will be new link created, okay. Now this link will exist. 4 is with 3, okay, 4 is with 2, and then 3 this 3 will go this side. So then this side will be, you see that this side 2 1 3 will be 1, and then right side, okay, 4 5 6 will be another subtree. This part is difficult. You are in a situation if there is any branch with it, but if there is no branch, then good. For instance, here inserting 7 is easier. So where we are going to insert 7 is going to insert right after here, right side of 6. Then we are getting 3 right. After 2 right, we are getting 1 more right. So that's, we have right over here. We have already right rotation, and we have already right rotation, and then we are getting 1 more right rotation. So then what is the process? After 2 rights, and it has no child, so usually right, then we do left rotation. That means 5 will come down, and 6, then 5 will come down, and then this 4 will be linked with 6, and 4 will be linked with 6, and 5 will come down left side, and 7 is on the right side. So now this is balanced, but previously, so this is AVL. This is AVL, but this was not AVL, right? 1 2 3, even or it is difference is 2, but we are not considering that this is AVL, because the next one, if we are another encounters another value, that will make difficult. So the policy is that as soon as we get 3 values, okay, we will make them balance, because within 3 values there is and these values are considered as distinct or not duplicate, okay. And then we are, since in a BST, the left value always less than root, right value always greater than root, so there is no duplicate, right? So BST, there is no duplicate, no same value. So here, whenever you encounter 3, then you need to make balance. So then now it got AVL. Anyone, any question?
Be on the first exam
Sorry?
next week.
Yes, we discussed this. I will cover it. Yes, question. Let me finish this.
If you use a regular EST over an AVL or a red black tree,
Sorry?
like when would you use a regular binary search tree instead of one of these? Would there ever be a case?
Yeah, we started from this lecture. So in case our tree grows, a BST grows linearly, that we will have our time complexity still linear time, right? In order to resolve that issue, in order to ensure that our tree will give us logarithmic running time, we will develop BST. We will develop AVL tree and then red black tree.
So there's no reason to ever really use a regular binary search tree then, right?
In case our data, if our we said that if our data grows like this, or we said 40, and then 40, 45, 50, we don't know that our data will come which order, right? A tree is like whatever you data structure you design, it should work for any kind of data, any number of data, any kind of data, right? We don't know the pattern. It can have like this way, right? So in that case, situation will be different. For instance, if you are asked to make number 1 to 1000, all numbers, and then BST will grow like this way, right? Linear order. Then what is the advantage of using tree? This is linked list or not regular data structure. Okay. So let us go. There are 2 more situations. Let me go through this. Then I will come back other discussion. So the third situation, this is case 2 they discuss. Okay. The third situation is this. If you read the book and maybe the video, there are a lot of discussions how to do it, but I know a trick. If you follow the trick, then it's easy. Okay. So here, so inserting, for instance, this word, inserting, you insert 16 and 15. Okay. So in our previous page, it was like this, right? So look at this here. It was like this. Remember this one. So we are our AVL tree is like right now this one, right? Remember this pattern, okay? And we wanna add 16 and 15 with this. So now we will face case 3. Okay. So here our case 3, rule 3. On the book they said case. Okay, I said rule. It's okay. So if you encounter, you see this is that we have from here right, and left. We have here right, previously right, or take 3. Okay, right, and left. Okay. Then you say right and right, existing to right, and then you got another left. Okay. So then another left. So the book has many discussion, and then I saw some other stuff that, but the trick is that follow me here, okay? You will never forget. So if you see like this way, it is getting this way. It's making triangle, right? It's trying to make triangle. Complete the triangle. Okay, complete the triangle. Okay, go this way, complete the triangle, right? And then do this. Remember this. So you have already this. You have already this. Right? This is right, and this is left. Okay, then complete this. Take this arrow. And 15 will go to 7, press 7, and 7 will come down. So 15 will go here, and 7 will come here, and then 16 is on position. Okay, so that is the thing on the right side. So it was unbalanced. You see that? So this is 1, 2, 3, 4, and this side is 2. So difference is 2, right? But now difference is 1. 1, 2, 3, and 1, 2. 3 minus 2 equal to 1. So it's just you remember that. Just you remember the trick. So if you encounter like the right, after 2 right, right, left, after 2 right. So previously we faced after 2 left, we got another left, then rotate right. Okay, and then next one, after 2 right, we face another right, then rotate left, left rotation. And then here, after 2 right, after 1 2 right, you got left. So then left, that means complete the triangle, okay, and swap. So swapping means this one, right? Swapping 7 with 15, okay, and this one will go down. 7 will come over here, and 15 will come over here. Please write this draw it in your book, okay? Then you will never forget it. Okay. So as we say on the right side. Okay. Similarly, if you understand, if you remember rule 3, rule 4 will be similar thing, and you will do something more. So rule 4, if you encounter left, and then right. Maybe I don't. Let me do it. For instance, if we want to. Send something like maybe you have 20, then 50 on left, right, and then 10, okay, and then another you got right, so left, and you got right, maybe 12. Then complete, it is 15, okay, it is 15, okay, and it's a left rotation. Then do the complete the let me draw a good picture so that 20 and then 15, so left, another 10, left, and then you got 12. This is right. Okay, so it is going to be a triangle, right? Complete the triangle, okay, then complete the triangle, okay, complete the triangle, go up, and then swap over here, then 15 will go, for instance, here. So then changed one will be like this. How can I write? Okay. 20 will go here, and then here 15 will go here. So this 15 will go here, and then 12 will come here, and then 10. We are not touching 10, right? 10. So this is the modified one. So then if you rotate left, and then right. So left, right, then complete the triangle, the or A triangle should be right. In English better than A triangle, and swap. So since swapping, it will need to take another variable, temporary variable, to hold this data, this value, and then you got the situation. So these are the 4 cases. In order to develop an AVL tree, we need to follow these steps. Okay, let us recap quickly. So left, 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 then right rotation, right, right, and then you are facing another right, so left rotation, and then right, right, and then you are facing left, then complete triangle. Okay, this right, right, left, and left, left, right. For instance, left, left, and then you are facing right, and then you will make the swap go up, make the triangle, and then make another face. Does anyone any question?
Can you go over rule 2 again?
Rule 2.
Can
Okay.
you draw it out?
Yeah, left rotation. For instance, right, right. For instance, here. Number 2. I can give an example. So right, 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 right. So for instance, you got 1, and then 2. You have right. Okay. So then 1 is just right, and you have right 2. For instance, it is good, even it is good, right, right, and then you are getting maybe 1 more right. Okay, then you have right, 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 right. So take this 3, maybe 4. Take this part, make a left rotation. Left rotation. This will it will go this way. So then it will become 1, and then 3, 2, 4. So for instance, this one. So this one initially it was unbalanced, right? For this side length is 0, and this side length was. Even whenever you see is unbalanced, make it balanced immediately. Let me go back to the original slide, the first slide. So this one, is it balanced? So this right side is length is 0, right? And the left side length is 2. The difference is 2. So as soon as this is unbalanced, make it balanced. So this is left, 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 right? Go right rotation. You see that this one, left, left, left. So go right rotation. If you go right rotation, okay, that means it is a string. For instance, this one string, string. And then it will go right side, and 2 will be middle, center, and then this one is left side. Okay. So for any situation, if there is unbalance, make it balance immediately before you face the next one. Okay. So here that I said oh no, where is my slide? I think I skipped one. I think immediately actually we need to do that. First of all, we need to do this one. This is not correct actually. So here, right, right, even if 2 right. So here, if we consider this is, if there is no branch, okay, I was considered that with this branch coming from this side because it will be misleading. So this branch is, left branch is 0, right? And right branch length is 2. Only this is, if this is the tree, then still it is unbalanced, right? You start from 1 is fine, then 2, you got 2, then 2 go right side, and as soon as you get 3 will go right side of 2, then it will be make unbalanced, because if it is starting point, so then don't go, so if it is part of another, then it may be fine, but If it is individual, then this side is 0, length 0, and this side is length 2. Then 2 minus 0 equal to 0, 2. Balance is, difference is 2. So this is unbalanced. So right now we need to make it balanced. So right. So even if you are not getting third right, we need to make it balanced. Okay, so right. If you do right, then what we will do? Left rotation, right? Okay, so then here that means if rotation, that means here, then 2 will be lead, 1 will come here, and 3 will come here. So that in that case, if it is an individual, even you do not look for 3 L or 3 R. Okay, so if you understand AVL tree, then our understanding our red black tree will be easier. So in our next lecture, this we will be at almost our test will be done by this time. Our lecture time, there is no lecture, but there will be test. Okay, and you know the test policies and then other things, right? So this open book, open note, and so let me give me 1 more second. Let me see if there is another situation or examples. I think it has the other cases, but description. If you understand these 4 rules, please write down the 4 rules. Okay, you will need it for red black trees. Okay, that's all for tonight, and give me a few more minutes. I will take the attendance, and if there is any discussion about the test. So test question, there will be 6 or 7 questions. Okay, I will give you exam paper. You don't need to bring paper. That bring your pencil and books, but please study. Otherwise, you will see that all the questions from book or assignment, but you will not get time to complete it. If you study, then you will find maybe you can complete in less than an hour time. As soon as you do, you can leave. But if you start studying or understanding during test time, you will not be able to complete. It is challenge for writing open book exams for us. Okay. Does anyone has any question about test? Okay, then we can wrap up. Thank you so much for